Thank you. Good morning to all. So first, I need to thank Sona Institute of College for giving me this opportunity to talk about the covalent organic frameworks before you all. And I also extend my thanks to Dr. Shankar Narayanan, who gave me and suggested me to this institute, and Dr. Sridhan for making this happen smoothly. So with all the things, let's go to the thing. So today I'm going to talk about covalent organic frameworks in separation and energy storage. So today my topic will be based on what is covalent organic frameworks and why it is being so widely and popularly used in different fields. So it has been just 15 years from the introduction part of the covalent organic frameworks. So, but it has been replaced many materials in many fields, right from the materials of porous separations and to the proton conduction or batteries and to the drug delivery. So what is the significance and the importance of COF in these fields are going to be discussed today. So before you talk about covalent organic frameworks, I think it's noteworthy to introduce to both great legends who started this field. So he is Professor Yagi. He's the one who introduced the covalent organic frameworks and metal organic frameworks into the chemistry world, to the research world. So he's the one who first prepared the borate linkages, and from there it took off to the various levels and various applications. And he is the other one is the Professor Fraser, who is like 2016 Nobel laureate. So he's the one who started exploring covalent organic frameworks applications, and from there he has modified the covalent organic frameworks and applications, and he's widened up the applications. So I like to introduce them about the covalent organic frameworks. So next is like, what is covalent organic frameworks? So covalent organic frameworks is a class of polymers that enable construction of ordered skeletons and porous structure. So the first covalent organic frameworks that was formed is the borate one. So covalent organic frameworks is an organization is a polymer connecting a smaller organic units. So with a well-connected structure is very stable, and it forms a like 2D, 3D structures with definite porous and rigid porous structures. So this is the basic common phenomena of covalent organic frameworks. So, but what is more important about and what is the advantages of the COF is, over zeolites or any conjugated or polymer membranes, it can be like very rigid. The porous is very rigid, and the stability, it is highly stable in all harsh organic solvents or in all over the pH range. So that is the great significance of the covalent organic frameworks. So even if you immerse this COF in acidic or basic solutions for a week, it is very stable, and it can be used for the precise separation. The separation of length is selectivity is very high, and it is made up of only low weight carbon, hydrogen, oxygens, and boron in some cases. So it has a low density and high surface area. So high surface area is like how you calculate is like you calculate by adsorption of nitrogen molecules on the surface and the active sites. So based on the active sites, then the surface area is calculated. And you can prepare a very wide range of covalent organic frameworks by incorporating different functional groups, starting from the organic easily available. So you have to select two organic monomers which can connect by a simple one-step reaction, and these form a single layer of structure and which can be stacked in different areas. So each layer stacking is held by hydrogen bonding or pi-pi stacking or electrostatic interactions. So these makes COF very stable. So among this, 2D structure is more stable, and it finds applications in various fields. So in another way, the easy way to design is like to select a monomer. So this is very important, which decides the pore size and also the geometry of the thing. So based on your applications, you can select the monomer, reaction conditions, and then you can predict the pore size and the symmetric of nature of the resulting COF. So in this, like here, even the length of the chain will decide the pore length. So if your length is short, it will be like if you wear it, and this will be the homoporous. When you even want to get a two different pore structures with this different fascinating symmetries and thing, you can arrange to this. So this helps in absorption or storage in separations and in semiconductors in all over the applications. So here the common reactions are there. Usually first the borates are seen. So boroxine, borate ester or borosine are all usually formed. So but this has a water stability problem. So hence imine, amide and hydrazone and even azo groups are even formed at this. So this ketoenol tautomerism helps in the stability towards the water and hydrophilic groups. So these COFs are highly stable in hydrophilic than the boric ester. So again, there is a, when you form the covalent organic frameworks, it can be arranged in two ways. One is eclipsed and staggered conformations. So when you go for the eclipsed conformation, it will be a large and uniform porous, but when you want a very precise and low porous structure to selectively absorb or separate the smaller molecules, then you can preferentially go for the staggered conformation. But whatever the conformation formed will be based on the reaction condition and the monomer you choose. So it strongly depends on that. So tuning the structure and tuning the linker, tuning the pore size is more important in the covalent organic frameworks. So while considering the organic polymers that been saying, they have the pore size, but it's not very rigid and it's very big, macroporous, more than 2 nanometer. So, but in the case of covalent organic frameworks, it can be microporous or it can be mesoporous. So microporous is less than 2 nanometer. If it is greater than 2, it can be mesoporous. So you can just tune that one. And in case if you have like if you want to add some functionalization of it. So for example, when you consider here, you can modify the R1. So depending upon the applications, for example, when you want to use a chiral center for catalytic reactions, or when you want to for the isomer separation, if you want, you can insert a chiral moiety in that so that it will act as a. If you want to go for the metal catalysis, you replace metal catalyst as a COF, you can go for the catalytic center. Or if you can even insert some groups, so which can attract the or which acts as a attraction point to the target molecule. Even in the, for example, even in this case for the drug delivery, even they are using it because by changing the pore size and by changing the pore nature of it. So when you modify the functional groups, you can even attract the chiral drugs and you can use it for the cancer therapy. So this is the synthetic strategy for this thing. So there are only two methods in a simpler way. One is go for the direct synthesis or go for the post modification. So the post modification is like, it depends upon the application. So the examples that I will show you like here. So here initially the original COF was synthesized with triple bond here. So depending upon their application need, you can introduce a group and form a single step reaction. So the ordinary direct step will be a single step and this will be a two-step reaction, and that's same way here. If you have a free azines here, or you can have even OH groups here to attack the other alcohols or something to insert in it. So these are the few reactions. So, but this reaction will never affect the COF structure. So the only thing is, but it may decrease the crystallinity depending upon the group that you add. But in most of the case, the crystallinity is like did not alter much, and only the pore size reduction will happen. And this pore size reduction will enhance, sometimes we will enhance your rejection and your target to achieve your target. So maybe in future slides, we will see in that all the things. So the synthesis, when you come for the two things, we have the problem, we can say like a hurdle for the covalent organic frameworks. One is the stability towards the moisture content, because in whatever the application you take, there may be a slight water content or moisture for it. So in that case, the borate ester, the initial one, the COF that was synthesized, was not stable towards the moisture. So that's why they have moved on to the amide and thing. Amide is so rigid and it cannot be used for the practical application. So imine linkages has been came to the fracture. So the ketol enol trans tautomerism helps to for the stability. It enhances the stability and also it is almost water stable. So even if it is like for a long time, it is highly stable in towards moisture and hydrophilic, and therefore it can be used for the application process, including where even hydrophilic applications can be done. So another one hurdle is like the synthesis. The synthesis initially, the cough powders or synthesized will take minimum 3 days to 7 days only at high temperature, and you have to use harsh organic solvents. And it should be purely in the nitrogen atmosphere. So this will give you after drying, and even the separation after washing process is like difficult because you have to use oxalate extraction for 3-4 days to get a pure organic frameworks powder without any impurities. But now, so this is one really difficult to make it as for the industrial applications, or if you want to go for real-time applications for whatever you use it, you have to reduce the reaction time, because you cannot wait for 7 days for one reaction to happen. So that's why, like, then there came an alternative of like mechanochemical sink, or if we're adding a co-agent, because in this method we use only acetic acid at different concentration as the catalyst, so not much catalyst are needed for that. But in this case, sometimes it may be catalyst free and very quick in 30 minutes. And other thing is, they have even used different ways and different catalysts like trifluoroacetic acid or methane sulfonic acid and paratoluene sulfonic acid. So these are the acids they have done, and this one helps in molding also. So this, you can mold it to different structures, tubular structures or whatever you want, or it can be a flat membrane. So it is very easy. So in that way, I think now the COF has synthetic procedure has been very muchly reduced to minimum 5 minutes to maximum it's 1 day, or like within 12 hours. So it has, and they have used the UV light, microwave synthesis, and all this one, most of them uses very eco-friendly solvents, not the harsh solvents, because if you go for the original this Pyrus tube method, you have to use dioxane or mesitylene alone. You don't have much eco-friendly solvents to be used. So it's very organic, harsh solvents are used. But now it's like totally different. So you can little bitly reduce and form a ethanol is also being used, and even solvent free is going on. So it's going through the green chemistry synthesis, and it's very rapid synthesis also happens. So with this, all this like thing, now we are like going for the applications. So when it happens to applications, so this the major properties of this porosity, robustness, and the high surface area, low density. So with this, it can be used for the various applications, right from the gas capture, or maybe biomedical applications like drug delivery or cancer therapy, or like in the material. Is okay.
Extra sweet also.
Sorry, ma'am. I request the participants to mute your mics. Thank you.
Okay,
yes, ma'am.
I'll continue. Yeah. So even the batteries and like everything is being done it. So when you want to, so now like from the powders to how it is applied to different molecules, how it is modified to. So that's why we are going to discuss here. But here I just take 3 applications for gas capture and the membrane separations, and for the batteries alone, I'll give you the short introductions about the 3 and how it has been developed now. So when we go for it, the initial one started with the adsorbent. The cough powders has like been used for the adsorbent for various gases like carbon dioxide, hydrogen, methane, ammonia, and so on. So now, like due to the current situation, we are in a situation to control the CO2 emission and to store the hydrogen one. So in that case, or nitrile and methane storage. So towards this environmental application, the cough was directed towards that, because it has a large surface area, it can attract it, it has the pore size, so we can target the molecule and when we can intake it. So when it intakes, it takes a large capacity and it can store it for a certain period, and then it will be slowly deabsorbed. In the case of CO2, even they have tried for the CO2 conversion. One, it is adsorbed, it will be converted to other things. So the possible way to remove is, this is the possible mechanism. How this happens is like maybe hydrogen bonding between the absorbate, and absorbent is the one that we have. So otherwise it may be acid-base interactions, but size interactions. When it is going for the dye or like larger organic molecules, when you want it, it mostly depends on the size effect. The larger molecules will be retained and only small molecules will be separated. And it may be with the aromatic pi-pi interactions. So these are the basic interactions which helps to obtain the target molecule. So when you consider the gas capture, first we'll go for the carbon dioxide capture. So actually the COF has replaced all the porous materials for the carbon dioxide and the gas capture, similar gas captures, because it has the highest uptake of like more than 1000 mg per gram. And this is possible because the linkages. So when you add the amide or carboxylic group in the side chain or in as a linkage, so this will have as a this acts as a CO2 philic groups. So this can attract the CO2 and hold it with it. It can bind it to that. So binding energy is high. The one of the severe problem in the CO2 capture is when you selectively absorb CO2, the nitrogen is also present. Even if you take the atmosphere, the nitrogen is also present in certain, even if it is industrial waste, it will be a moisture and nitrogen will be present. So the nitrogen and the CO2 is almost similar radii, and they also have the equal binding energy with the organic groups. So there is always a, so in this case, the major problem was the selectivity. How selectively it can absorb only one of the carbon dioxide, leaving the thing. Even so, when you add these groups like carboxylic groups or azo linkages, the azo linkages also is known as like nitrophobic group, because it has it is like mostly it avoids the nitrogen, and it because of the nitrogen lone pairs, so it just attracts the CO2. Even if you're present CO2 in 10% and 90% of nitrogen when you mix it, so this group and the azo group can effectively separate CO2 and store it with that. So this has the remarkable setup for the CO2 capture. So when you think for the methane capture, same way in the methane, so same way the natural gas. So it's very important for the for us for the current period. So in this case, if it is very low densities, so it has to be trapped well. So in that case, absorption was the best method to trap the natural gas like methane and keep it. So for this, they have tried many materials before, right, from the zeolites or other porous materials, but it was not that effective. But when you consider the COF, especially when you dope with lithium ions in the linkages of after doping it with that, it really absorbs, like the binding energy between the methane and the COF has increased significantly, and then so it has also obtained the highest uptake mark. So till now the other materials could not surpass this remark. So another one is like, it's also a similar one, like hydrogen is also, so which is also needed for you like now. So so in this also the various different COFs have been done, but it is equally good to the metal organic frameworks and thing. So different kinds of linkages, amide, imine, borate are also used here. So, and this one mostly borate is used for this hydrogen capture absorption applications. So it has been taken different sites, and still now when you consider these three gases, I think the COF has shown the remarkable applications and process here. So same way, this iodine is like radioactive. It's very difficult to separate in this field. But in the COF, considering COF, it was very easy and practically applicable because of like van der Waals interactions and hydrophobic nature inside it. So the right choice of the linkers side chains will absorb the iodine capture, and then it helps to store it for a long time, even if it's fluorescent. So it has different applications. So the major thing is like we have faced the heavy metals. So like it may be a mercury or it lead or uranium radioactive things, or so all this has to be removed. So this was the another challenging application to be started it. But the ordinary COFs was like not that active towards the or did not bind well to that. So especially the sulfur based groups are anchored. This is called the mostly by post synthesis modification. So they anchor the sulfur groups. So this has been the best way to absorb the metals. So in this way, even the real-time application is possible because of this, because this imine with this sulfur anchoring groups is highly hydrophilic and it's stable in water. So the real-time application in the ecosystem is really possible with this, and it is even used now till in industrial applications. So all this is okay. As an adsorbent, it has been given a high storage applications, but the storage alone is not an end. So we have to go to the next step. So for a real-time industry applications, so these powders cannot be used in the industries because it's just an adsorbent as a powder. But even if you want to change the powder into membrane for using it in the industries, you have the problem of processability, because the two biggest strength is stability and insolubility of COF. And when it comes to the industrial applications, these two are the major hurdle for the COF to be applied in the industrial applications, because it's insoluble. So how to process as a membrane? Because you can just, as an adsorbent, you can just make a pellet and do it. But if you want to really go for the membrane applications in the industries for industrial cleaning and everything, it is impossible to make a membrane, because when you go for the processing, you cannot dissolve in any solvent, because usually the polymers, they dissolve in a low volatile organic solvents like ethanol, hexane and thing, and they just disperse it, and then they then make it as a thin membrane or thick membrane, and they use it for the separation. But in the case of COF, it is not soluble, and dispersion is not a best idea to do it. So thus we go for the different membrane synthesis. So this has opened this challenge opened the new era of this. So in the recent 3 years, the membrane synthesis, and mostly 2D membrane synthesis, because 3D is very hard to adapt to the membrane structure. So 2D overtook the 3D here. So here from now, like it started towards the membrane. So to be a membrane, it should be like, first it should be defect free. So if you have a dispersion in the solution, if you mean it may be a defect. And the thing is, like, it has to have the high permeability. Permeability means the rate of the solvent or any solute that flows through the membrane. So this can be faster because we have the ordered channels in the COF, but you can even tune it, so it's okay to, and even selectivity. As we said, the tunability of the pores is important, is very easy in the COF. You can even choose a microporous or a mesoporous. So it depends upon the, if you choose one benzene ring linker, it will be very less, around 2 nanometers. If you want a like mesoporous material, you can just even increase the length of the linker. So that will not be a thing. And stability is also not a problem. The problem is scalability and processability. How to process it. So how to move towards it is the one. Another one is like, another added advantage of the COF is it can be a single layer. Because when you take a polymer membranes, this very thin layer of few nanometer thickness will be defect. It is not a proper membrane, and there will be a very thick membrane will be used. So this one will reduce the permeability of the polymer membranes, or you have to go for the ultra porous or like mesoporous, more than large porous size. So when you go for the large porous size, definitely the selectivity will be less, because even the small molecule and the large molecules, everything will be passing through the membrane. So this disadvantage of the previous polymer membranes made us to move to the COF. So when you're focusing on the COF, so we have to just focus on how it is possible. So we have to change the synthetic method for it. So when you go for the synthetic methods, they actually adopted 3 major methods. So first one is mixed matrix method. That is like commercially available polymers are taken it, and the COF powders are used as a solvent. So this COF acts as a filler in the polymer. So they just blend it together and they make a membrane. When you make a membrane with the blended one, the fillers and the polymer, I mean the co-fillers and the polymer may not blend it uniformly. There may be some voids and defects of occurring here and there. And another one is the thickness is very high. But still you can control the thickness, but still you cannot get an ultra thin membrane, but you can get a freestanding membrane like here. So it's just a membrane without any support. And another one is like forming. So here you choose a very ultra porous any substrate, commercial substrate. There are many commercial substrates available in the market. So it's like you buy that and you take a reaction, you place a you do the reaction on the top so that the COF membrane covers the substrate and forms a membrane to it. So this it will have a support. But very important is the COF membrane and the substrate should have a good attraction. So only then it will be there. Otherwise, the COF membrane will be peeled off easily. So another one is like very layer by layers. We say it's like layer by layer stacking. So you can just plan and stick it. So usually you use low ethanol or hexane here. So this is very easy. Like you just, so depending upon the thickness that you need, you can just immerse it, repeat this cycle for us. So, and then you can get a final COF membrane. And this one is like very easy because after you're loading, maybe you can keep it at room temperature or you can even preheat it depending upon the reaction. So this was okay to do it. But it's okay, when you consider for the first gas separations, you use mostly these are the like mechanisms that it follows. The diffusion, so dissolution diffusion is only from the absorbent. So from that mechanism only we developed this. But here this is possible only when there's a pressure difference or concentration difference in that. So another thing is like depending upon the charged molecules when you use it, it may be Kunstler difference or surface diffusion. And molecular sieving is mostly depends. It is used in the dyeing industry and pharmaceutical industry because there you will get like two type of organic molecules with different size. So you need to precisely separate it. So in the, but the binding energy will be the same, but only the size effect is different. So in that case, you can use this way. So and not only that, even if you look for the gas, if you just want to separate the lower molecular gas with like for methane and if for propylene and like the hydrocarbons, in that when you consider, it is very easy to do with the size and molecular sieving effect. So this is the one example that I want to show you for the mixed matrix membrane. And this work is like is done by the Indian scientist Dr. Rahul Banerjee. He's working in Pune and he is also a direct student of Professor Yagi. So I think he is the one who is now from India is like doing a very good research on the covalent organic frameworks. You can even go and visit his website for a lot of, he is the one who introduced this ketoimmunol COF. So, and this is like very good stability. It is an actor and it can be adaptable to all the applications. So he even used this for the conductivity and for the drug delivery and also for the water treatment, desalination, or it may be organic nanofiltrations. I mean, like using the dyes in organic solvents, filtrations in organic solvents, and even in the gas separation. So this molecule is like, this is the commercial polymer. So you just blend these two and make it as a freestanding membrane here. So when you make it, but this has showed a good performance, but still the selectivity is being reduced when you come for the mixed matrix membrane, and even the permeability is like reduced because this membrane is like thicker one. It will be like few macrometers, so it is difficult to penetrate. It takes a long time to penetrate for the gas molecules to come. So in that case, the permeability will be low. But another one is, so when you consider, so these are the hurdles that when happening it, and you cannot even process it. So what is the next step? So that's why we go for the interfacial polymerization. So this is like a simple polymerization. So interface, that is when the two solutions, two immiscible solutions. So one can be a water, one can be an organic solvent. So when these two meet, this is called the interface. So the reaction will occur at the interface. So it can be liquid interface or liquid air interface. So it can be anything. Another thing is like this one is like it has been very important because it directly synthesizes as a COF membrane, as a film, nanofilm or nanosheets, and whatever the format you can get it, and it's a very thin because you can, depending when you dissolve it like low concentration, and it's like slowly the molecules diffuses at the interface and it forms. So once the reaction is finished, so you think like when the thin film is or the COF membrane is formed, so the further diffusion of monomers from this liquid 1 or liquid 2 will be reduced. So in that case, this we get a very thin membrane. So the thin membrane will cover this interface. So further diffusion of monomers will not occur. So that the reaction will be slowly stopped. So within 30 minutes, you will get a very thin membrane. So which is the most desirable for the industrial application. So this is the best way. So now in recent years, different kind of interfacial synthesis and how to improve it, how it goes, and all and different kinds, different reactions, but it also has some drawbacks because all the reactions cannot be done. So it has to be in the immiscible liquid. You have to choose a reaction, and monomer solubility is also important, and the reaction should occur in room temperature. So that is more important in this. So these are the certain challenges in this work. But still, it is just in a very infant stage. It's just in a baby stage now. So still, but there are few methods they have tried it. This one I like to say because it's a very simple reaction. It's all one-step reaction, but the way they have carried out makes a remarkable change in the membrane synthesis. For example, when you take here, they take an organic solvent, dichloromethane, and the water. So here they choose the para-toluene sulfonic acid. The choice of this catalyst is important because this one, when they mix with the amine, and these are both are taken in water, so this forms a hydrogen bonding with this amine group, and it forms that. So when the time grows, or when you increase slightly the temperature in a controlled way, the hydrogen bond between these two breaks it, and then this amine penetrates to the water layer of this monomer and reacts and forms a polymer. So when the reaction is slowed down, it's more crystalline and very thin. So that's, and even sometimes, you know, like they take a monomer 1 solution in water, they place a pure water, and then they take, a monomer 1 in a dichloromethane, and then take a pure water, and then they take the another water layer for considering these two monomer B and the catalyst inside. So in that case, what happens is, like from the water solution, it has to penetrate slowly to the water layer, pure water layer. So in that case, that penetration will slow down the reaction. So it will be very uniformly formed. So when it penetrates and the hydrogen breakage of hydrogen bonds occurs, so it will be all very slow process, but still it's a very effective process. Slow means it's like not that slow, but it take 1 day to go. So in that case, but you can get a very crystalline and neat and ultra thin and freestanding membrane, because ultra thin and freestanding is a very important criteria and attractive criteria in the membrane synthesis. So they think, and in this, like now this is another way, and another way that we actually adopted and we tried in our lab is this diffusion method. Here it's like simple. We designed the diffusion cell like this. It's like normally in the U shape. So here is like we place the membrane here. I mean the substrate. We place some substrate here, macroporous substrate. So and then we coat with the single-walled or multi-walled carbon nanotubes. So this will be in a reduced pore size. So one side it will be a macroporous and one time it will be microporous. So when the solution diffuses, it slowly diffuses and comes to the CNT layer, and after that we will add this layer. So the slow diffusions through the microporous substrate will form a very thin and uniform layer. So once the layer is formed, the reaction will be finished. So you don't want to, so whatever the concentration or anything, how long you do the experiment. So once the membrane is formed, the further reaction will be stopped. So this was very advantage of this, because when you get for the polymer, if it is very ultra thin, maybe it is not stable, it is not maybe high pressures or anything, it's not like stable. Another thing is it may have the defects, but when you check the COF, it's uniform, very uniform ordered structures, and even it is a covalently linked, so the even single mono layer has a high mechanical strength compared to the polymers. So this is how they prepared it, and this is the example, like even they have taken the SEM images to see how slowly it forms and finally forms. So first it forms as a fiber needle-like structure, and then it forms a clusters, and then slowly it changes to the membrane. And this is the one they have used for the dye separations. So here they have used acid fusion and nitrophenol, two sides. So it's for the organic, when you use it for the dye in the pharmaceutical company or in organic dyeing industries, the most important is your membrane stability. Your membrane should not absorb the dye. That is more important. It should, because that may damage or it may, because if you take absorption, after the absorption, when it is all the pores are filled with the dyes, definitely the excess dyes will be falling down. So that will not be an ideal separation. So the ideal separation will be must be based on the size. So that is most important while applying for the dyeing industries. So in that case, this satisfies well. So there is like, it's just acts as a channel to pass through. So when you tune the channels to the different thing, depending on the balance, because here NP is just like only 0.8 nanometer in the length, and this is like around 1.8 to 1.8 to 2 nanometers. So in that case, so when your pore size is 1.2 nanometers, so the dye molecules or any organic molecules higher than the 1.2 nanometer will be stayed up. So only the new. So this will help you to find applications in thing. Another one is the same way, the casting method, they have done it, and this one they have done in the other direction. See, rhodamine B, and rhodamine B is also vastly used one, and it is like pink color, it's like environmentally hazard, so we have to separate that from that. So in that case, this was also they have tried the applications, real-time applications, and this worked well. And even after 2-3 uses, it was good, because it's very easy when you immerse in water. Since after the membrane, if you want to wash it, it's very easy comparable to the other membranes, because when you immerse in water or ethanol, whatever may be, depending upon it, the dyes are highly soluble, so it will soluble it, and the membrane structure will be the same. Even if you take the surface area measurements and the XRD, it will be the very similar to the freshly prepared one. So it can be used again and again. Another one is, so another one that I just wanted to tell you is about this one. This one is also like simple Lewis acid catalyst reaction. This reaction is very, very fast. Actually, these powders were obtained in long before, but now they have this last 2 years it has attracted many attention towards it, because this is mostly hydrophobic cough and with large pores. This is the only imine cough that can be formed within 5 minutes. So within 5 minutes, you get a very, very thin layer of thickness of like 5 to 10 nanometer. But the use of that layer is like really difficult. So in order to gain little bit thickness to mechanical strength, they carry out the reaction for 30 minutes and for 3 days. And they compared with the dye rejection and with this. So in that case, the dye rejection of the rhodamine B was good, but the problem was in the water permeances. Even it has a very large pore. So the pore size is around 3.2 nanometer, but still the water was like the water permeances, when you check it here, it's very, very low. It takes 1 day like for this experiment to go ahead. So this was very poor, and it had as a, so there was a like, why there was, usually when you have a large pore size, the permeance should be faster, because it penetrates faster, and cough is stable, so it should not have any problem in that. But this cough reacted in a different way. So again, they have even modified it with it's the original cough with the methyl and ethyl group. So when you add the ethyl and methyl group, definitely the pore size decreases, and even it increases because the pore size decreases, but it helps to enhance the rejection to a certain extent, but it never enhanced the water permeability. It has a very poor water flux. So in that case, like, we thought to modify this one another way, and we thought to do for the organic solvent filtrations. So not only the dye filtration, you can do it in a real industrial applications. They don't always, your organic waste is not only the water, it can be any organic solvents or a harsh organic solvents. So we try to synthesize it in a diffusion cell that I showed you. So we coated the single wall, the CNT film. Here we loaded the catalyst, and with the through slow diffusion, a thin layer of cough was formed. So this cough is, the use of CNT here is to increase the mechanical strength, because here we did the reaction only for 10 minutes. So in 10 minutes, like, very narrow, very thin layer of cough will be formed. Only one day, mono layer. So with that mono layer, maybe it may not have the real mechanical strength for the real-time application. So when you use CNT or graphene oxides, even they use graphene for the backbones to increase the strength of the cough mono layer. But when you prepare in a multi-layer, you don't need the help of graphene or carbon nanotubes. So in that case, we did in 3 different solvents, like methanol, THF, and Xn. So it's like aprotonic solvent, polar aprotonic solvent, polar protonic solvents, and apolar solvents. In that case, it has a high permeance for the organic solvents, but the dye rejection is different in different solvents, because usually all the coughs will be carried out, the dye rejections, mostly the research has been in the past, it has carried out in water, in ethanol, and methanol, and all 3 will be the same, because because the size selectivity is the major criteria for doing the separation. So if it is a size, the solvent doesn't matter, but this cough behaved in a different way. This one is like, depending upon the solvents, the rejection rate varies differently. So then we came to understood that it's not only the size matters, the polarity of the dye or the polarity of the solvent, and even how the solute and membrane interaction occurs, and solvent and membrane interaction is also more important for it. When you take the THF, like, it is a weak, a basic thing. So when it is weakly absorbed on the membrane, so it can penetrate very faster. But when you take a methanol is like hydrophilic. It has a OH and it has a polar interaction with the protic solvent. It has an interaction with the imine bond, and it has a good solubility also matters. So in dyes, all these dyes like Sudan 4 or Merithrone B, Erythrone B, or Rose Bengal. These are the size ranging from like small, this is the smallest dye of like 0.8 nanometer to this 2.3 nanometer. So all these dyes are very good solubility in methanol. So these 3 interactions, solute, solvent, and membrane interactions are higher. So in that case, the methanol permeance is also slow, the flux is also slow, and rejection is also very low. But when you take the THF, it has a weakly absorbed and it fastly penetrates to it. But still, when you compare it, THF has higher molar volume than methanol, but still the interactions plays a main role. So thus it opened the new direction that not only you cannot just focus blindly on the size, you have to focus what are the interactions that's going on between the solute, solvent, and the membrane functionality. So these 3 also plays a major role when it comes to the real-time applications for the industrial applications using the organic solvents. So next, with this, like, we'll move on to the electrochemical applications. So here the cough, like as I told you, we can alter it, design it by adopting donor and acceptor molecules here. And so in that case, it has been used in a different applications like capacitors or water splitting or sensor or solar cells. But like now I'll show you like the batteries, because the choice of battery is like, the battery is very important. Now the storage of energy storage is very important nowadays. But the choice I choose it here is, in recently the batteries has grown as a very large, because initially only for the solar cells and supercapacitors were used. But now what is the need for the COF in the batteries? Because it is like 2 different dimensions, but they have merged it together. So what is the need and what is the next? Even the scientists named COF as the next generation batteries. So what is the reason for that? Is first they use the inorganic transition metals for the batteries. So in that case, the major disadvantage of the using the metals is the transition states. When there is a change in transition state, it affects the redox reaction cycle. So then they move to the organic compounds. In case of organic compounds, it is like smaller organic compounds, but it has a poor cyclability and it's like the solubility. It can soluble into the electrolyte. So these two major hurdles were faced in the battery applications. So thus they moved on to the organic frameworks to incorporate organic frameworks under this. This organic input, it can be used in any type of electrolyte and any type of batteries. So this was the added value for the thing, for the organic frameworks to include it. So it's only the very recently it has been used it here, but it has emerged in like the other way. Not only lithium, because among the batteries, the lithium ion batteries is the widely used now, like from your cameras to mobile phones and laptops, everywhere you see the lithium ion batteries, it's widely used. But the another danger is also there for using the lithium ion batteries. You may get insufficient lithium ion in future. So in that case, if you want, like, the scientists are really eagerly attracted towards the sodium ion and potassium ion. So even if you take the publications, I think in recent years, the sodium ion and potassium ion publication has been very higher. So, and they have even coined the term as an COF as a next generation batteries. So in this way, it's rapidly developing, but still it is only in a very, very first stage and early stage now. So it has not been fully developed, fully the COF has not been used, but few COFs that have been used shows an extraordinary performances in the lithium ion and sodium ion, or even in the mixed ion batteries. So in that case, just I want to show you like few examples for like lithium, sodium and potassium ion batteries. So when you go for the lithium ion batteries, lithium ion batteries is the widely used, and we also have a thread of exhaust of lithium ions. So, but still no one can replace the lithium ion for now. But the only one disadvantage is like dentimeter growth of the lithium ion batteries, because when you use it, it forms a layer, and that dentimers will be dissolved in the electrolyte. So the circuit is like broken, and it suffers a cycle, repeating cycles and things. So in that case, they have even tried different additives, but still the problem occurs. So in order to create artificial solid electric mesophase, they just incorporated the COF for that. So the COF properties helps to
Participants, please mute your mics. Mr. Deepak, your mic is on. Yeah.
Yeah. Okay. Okay. It's okay. I can carry on. So in this case, like they have just thought an idea of incorporating the COF accidentally, but it became a huge attractive topic nowadays among the researchers. So in that case, like first the example is they have used this one, like bis trifluoromethane sulfonyl imide. So this one they have used a simple COF with this single monomer nitrogen, but this one is like generates like this one is like we can say that this CTF COF is lithophilicity. This is the one that gave a surprise to the researchers, because it was highly lithophilicity. It attracts the lithium ions and it produces LIF particles. So this one, since it is like ordered pose, this added the advantages. So it's also attracts the lithium ions. The particles are evenly distributed. Even if they have used the airlaid paper here, but the distribution was not even. But when you use the COF, it is very evenly distributed, and even it adds the high voltage and the number of cycles is high up to 700 cycles. So this is the first one, like, to explore it to the way. So this one, the nitrogen group, it has shown to be lithophilicity, attracted the researchers to do more on research on the COF based batteries. And the other one, the similar one, is like they took this simple trihaldehyde and diamine group, and here also they have tried it the same. The nitrogen content of this increased the thing, and the same way when you see the dentimers, like metallic, even in the both the ways, it's like evenly distributed and it doesn't interrupt it, so it can be coiled up to they have tried in different milliamperes thing, but still it has a very high performance than the copper or thing, bare copper substrate. So this is the one, another one. These are two major things that has been attracted in the thing. But this COF, they thought first it will be suitable only for the lithium, but now the sodium and the potassium has overtaken the lithium nowadays, because there should be an alternative for lithium battery. It's the right time to look for the alternatives for the lithium. So in that case, they have the suggestions for two. It's one sodium, another one potassium. The sodium suggestion is because they have the same reaction potential and electron density and cyclic. It's a little bit lower than the lithium, but still it can act as a potential replacement for the lithium ion batteries. And still the mechanism and the further research has been in process. Hopefully in the next year, maybe we will get a lot of batteries and research oriented and a lot of new COF electrodes based on this. So here they have found the two methods. One is like introducing the C double bond O groups here. In this way attacks the sodium ions. So this one also like has a high specific capacity, and it is like stable for up to 100, more than 100 cycles, like around 1000 cycles. So this one is like, here the main thing is the thickness of the COF thing. So they just checked first. This paper mainly deals with how this reaction occurs and what is, so increasing the thickness and decreasing the thickness, how the free radical intermediates are formed or been. So the thickness is the main criteria for this reaction. And the one, like, so when you want to decrease the thickness, what else we can do? So we can preparing monolayer is okay, and how to deflame it. So when you want to deflame it, they just go for exfoliation. So they just cleave the single layer, very thin layer of the COF, and they make it as an electrode, and this also do it well. And this also increased the decreased the band energy gap, and it increased the performances. The other one is the so the second alternative, they look for this potassium. The potassium has little like negative drawbacks of like low Lewis acidity and higher mobility, but still they strongly believe that the potassium can be the second alternative for the lithium ion. And this is like very few papers have been reported on the potassium in the recent years. So hopefully this will get bigger, higher, attractive and green topic in the future years. So when you take it here, they have included the fluorine electronegative atoms, because when they use the fluorine gap, this electronegative atom helps to reduce the energy band gap between the reactions. So this actually helped the COF membranes to improve the performances. So the other one they have done is like using the CNT. So here the use of CNT is totally different, because for the membrane, if you use the CNT, it will be for the mechanical strength. But here the CNT will expose, is actually enhanced to expose more active sites, and it also shortened the ion and electrolyte diffusion distance. So this one helped for the thing. So, and it was this material was the stability also was enhanced than the normal COF, and the performance was also increased because COF is like poor conductivity. So somewhere you have to improve the conductivity of the thing. The choice of monomers is also there, but still it faces the COF is not extremely conductive to be used for this kind of applications. So they have looking for the alternatives like carbon nanotubes or graphenes and multi-walled carbon nanotubes to enhance the performance, and to how to incorporate is another problem. So these are like will be the future research to undergo it. So when I get the summary, so we started with the COF replacing the zeolites and metal organic frameworks. So the COF first initially it was used as the adsorbent, and for for all the environmental applications like gas capture or radionuclide or heavy metal and toxic pollutants. And from there we moved to the membranes, how it real-time industrial use, how we can use membrane as a real-time applications for the industrials based on organic solvents or maybe the water. So in both the ways, and how is for the what are the difficulties and how to improve the strategies. And then we moved on for the batteries, how to improve the COF. So far this is the 4 methods that they have done to improve the conductivity of the COF. So maybe exploration or maybe incorporating electronegative atoms and so on. So, but still there are a few challenges to that. So when the membrane and the thin film carbon, only the 2D COFs has overtaken it, but the 3D COF as adsorbent, it stopped as adsorbent. It cannot go for the further research. So still, what is the mechanism and what to do is still remaining. And then even still now it's difficult to get a single crystal. A single crystal of COF is a little difficult one. And when you go for the membrane synthesis like interfacial, it limits the monomer choice because it should be within the solubility of thing, and the reactions is also because when you go for absorbate you have a lot of linkages, but when you go for the interfacial polymerization all the reactions cannot be done in a room temperature or at the lower temperatures. So these are some restrictions are there, and further things has to be done to improve it. And when you go for the other side of the applications, yeah, the conductivity is the major problem for the COF. So how to improve the conductivity is the most important one for the electrochemical applications. So with this, I finish it and summarize it. I think so. Hopefully, I think you will be having the good knowledge about. It's just an introduction I have given you that I have learned, and then so far I have done in my research. So maybe if you have any doubts, you can contact me, or you can just go and read. I suggest you to go and read a lot of papers there, because there are now there are a lot of papers obtained here. So I'm here because of the 2 institutes that I'm really thankful to it, the KAIST, South Korea, which offered me the PhD, and this is the where that I met a lot of Nobel laureates, and this is the place where I met Professor Yagi and Professor Stoddard, where I just got impressed about them, about the research, and then I just choose the covalent organic frameworks. And thank you for Professor Jin, who just changed me from the, I was also just synthesizing the powders and things. So this is the lab that gave me the another directions for going to the current trend, changing of membranes and adapting with the industrialization and application. So I like to thank you all for listening it. I hope this will be at least give you a small opportunity to know the new things to you. And thank you. And if you have any questions, let me know.
Thank you, ma'am, for your informative session. And I hope that the participants would have learned something new from this session. Now, I request the participants to come up with their questions. Now, the forum is open for the discussion part.
That's okay.
Yes, that was a wonderful talk, ma'am. Thank you. And participants who want to ask questions, you can unmute your mic, and then you'll be able to answer. You'll be able to ask the questions to the speaker directly. Ma'am, I have a question. So we were talking about this nanomaterials, particularly the carbon-based materials, so CNT, graphene, all these things, and then this COP. So do you see these materials replace these lithium-ion batteries in future?
Yeah, because I think when you go for Yeah, because I guess like there are some actually it's like two few professors like they told me like the graphene cannot be done it same way like they had a dilemma on it, but when you go
Yes.
for the publications there are a lot of papers based on the graphene. So it because the only thing they say that because well forming the if it is in a staggered stage or eclipse state, active sites may be buried inside. So only few active states may be visible. But when you use these kind of supports, so it will be uniformly staggered things, and so that all the active sites are exposed. So in that case, yeah, it has some advantages towards it. That.